Alrighty, so for this video, I want to talk a little bit about projectile motion. And so what I've done here on the board is I've drawn a little diagram of an object undergoing projectile motion. And so remember, projectile motion is, when you fire or shoot or throw something at an angle versus, going straight up or straight across like that. And so if we do that and it goes at an angle like this, it's going to undergo some parabolic motion like that. And just to keep things simple, I'm going to assume it starts on flat ground and ends on flat ground. And so what I've done already is I've decomposed this velocity vector right there into its component parts. The vertical part is v sine theta, the horizontal part is v cosine theta. And I've also written something useful that we know, which is not the velocity. It's not that the velocity is zero at this highest point, it's that the vertical velocity is zero at this highest point. Because keep in mind, the velocity in the x direction is constant. It's the velocity in the y direction that changes. And at the highest point, the velocity in the y direction is zero. And then along with that, I've also written the kinematic equations right here. And so really the idea behind projectile motion is to take these kinematic equations and then convert them into their vertical and horizontal components and see what, kind of see what you can get out of them. And there's really a couple things that you want to know, usually for projectiles. How far it goes, so it's range. How high it goes, its height, maximum height. And then how long it's in the air for. If you know those three things, that's really everything about projectile motion. And so let's see what we can do. So the first thing is the easiest thing actually, which is because the velocity in the x direction is constant, we know that the range then, because that velocity is constant, we know we don't have to worry about the acceleration because the velocity is not changing. And therefore, I can use this top equation, that delta x is equal to velocity times time. Remember, this equation only applies when the velocity is constant. If you ever have acceleration, you're looking at these equations, but we don't. At least not in the x direction, we don't. So therefore, we can use this top equation. So it's really easy. The range then, how far it goes, the range then is just equal to the velocity in the x direction times the total time that it's in the air. So the range is equal to v cosine theta times the total time. Okay, so that's our range. The next thing, like I said, the next thing I want to know is maybe how high it goes and how long it's in the air for. And so, when we're doing projectiles, there's multiple ways of analyzing projectile motion. You can use different approaches to get the same answer. The way I do it is I look at the second equation, or depending on what they give us, really the third equation too. But either way, I use the second equation to find the time that it's in the air for. I know that the velocity in the y direction is 0. And so therefore, I'm going to write this second equation in terms of the y components and set it equal to a final velocity of 0 and go from there. So the final velocity is 0. And that's equal to the initial velocity in the y direction. So that's v sine theta minus, and I'm writing minus gt just to represent the gravity is negative in this case because I've defined the velocity as positive, and so therefore that's minus gt. Okay, and so therefore I can solve this in terms of the time to figure out how long it takes to get to the highest point. And so I would say v sine theta is equal to the gravity times time, and therefore time is just equal to v sine theta over gravity. Useful equation. And so I'm going to box this one, and I'm going to write this one over here. I'm going to write t, but remember, I'm writing t to represent the highest point. Be very, very careful, because if you solve for that t, which is v sine theta over g. If you solve for this equation, we can't see it, can we? Okay. If you solve for t right here and then plug it right into here, you're only going to get the range, you're only going to get half the range. So you have to double this time right here, because this is just the time for the highest point. This time is the time for the total range. So just be careful about that. And in fact, I'm going to write t, I don't know how easy it's going to be to see, but I'm going to write t 1/2 just to represent half the time. All right. Something else that's useful to know is the maximum height that we would get. So I'm going to look at this equation right here because I see that it has a delta x. Remember, the delta x is just sort of a placeholder to tell us about displacement. And so we can switch that around for delta y or delta x. It's just the displacement. Same equation, still valid. And so I'm just going to say that the velocity in the y direction is 0 right here. So that's 0 is equal to the initial velocity squared. So that's v squared sine squared theta. Last year I had a question, how do you know or why is it v squared sine squared theta? Because if you have a term, a term that's squared, you square, or an expression that's squared, you square each term in that expression. And so if v naught is v sine theta, v naught squared is v squared sine squared theta. All right, I'm also going to replace the acceleration with negative g, and so I'm left with minus 2g delta y. Okay, and now I can solve for delta y, but instead of writing delta y, I'm going to write h. I'm going to write h to represent the total height, or the maximum height, I should say, because that's what we've defined when we said that the velocity in the y direction is 0. The velocity in the y direction is 0 at the maximum height. So therefore, we have v squared sine squared theta is equal to 2g times h. And now I can solve for h. I can say that h is equal to v squared sine squared theta all over 2g. This equation, super, super useful. This is the maximum height equation. And so I'm going to erase this, actually. I'll just box it right now. I think that's the last equation we really need. So those three equations are sort of the way where I go with everything. Again, different ways of getting to it. You can use different methods, totally fine. This is the way I approach it. I will say this, just as sort of an aside, since a lot of you guys have either taken calculus or you're going to take calculus. Another way to think about this is that if we have some curve right here, and we take the derivative of this curve, and we set that derivative equal to 0, that's going to represent this point right here at the very top, right? The derivative right here is equal to 0. And so if I take the derivative of this equation and set it equal to 0, you should see that we end back with this equation right here. Derivative with respect to time, by the way. But you should see that I end with, I can solve it and end up with this exact same equation right there, that v sine theta g. So just to show you. So we could say, instead of x, remember I'm using y, so I'll just say dy over dt. Set that equal to 0. Dy dt. Okay, so therefore I'm left with v. And I'm going to write the sine theta in there just because that should be in there. V sine theta. If I take the derivative of this part right here, I'm left with just gt. Or it would be at, but I'm using gt, so I'm going to put a minus right there. But notice, so my equation would be 0 is equal to v sine theta minus gt. So just notice that this right here, I get the exact same thing as I have right over here, using a little bit of calculus. So just as an aside, you don't need to know that or anything, but all I did was just, I took the derivative at its highest point. All right, guys, so that's our review of projectile motion.